Assalamualaikum warahmatullahi wabarakatuh. Selamat malam. Nampak skrin tak?
Nampak tuan. Saya nampak tuan.
Nampak. Okay. So the topic today is for some very boring, because it is engineering. I will talk about, we have completed the subpart A. Now it's subpart B, which is flight. Then later we continue with subpart C, subpart D, subpart E, F, G, and H. H is the latest where there is a requirement for the EVs. So let's look at the subpart B first. So I'll record this. I will put it in my YouTube channel. So what we're looking at tonight. So the Airworthiness standard subpart B, which is flight. Anything to do with the flight of the aircraft will be in this subpart B. Subpart C later is structure. So subpart B is flight, about aircraft performance, flying qualities, and you can see the table here where I show you the basic of this subpart B is the IQ Annex 8 Part 3. Sorry, there was a mistake there. IQ Annex 8 Part 3, Chapter 2, which is general performance flying qualities. And then the state, most state, for example the US and the EU, publish their own, they call it national standards on this airworthiness, and they publish for large transport aeroplane Part FAR Part 25 in the US, and the EASA CS Part 25 at EASA for the EU. And they don't call Chapter 2 flight, but they name it as Subpart B flight. Then I also will show you the unmanned aircraft system. They still call it Subpart B flight. And also we do have the larger unmanned aircraft system, which is the candidate for RPAS, and that is also Subpart B UAS operation. So let's look at one by one. So Part 25, first in the first subtopic is general, and second we have subtopic on performance, and then another subtopic on controllability and maneuverability, and then trim, stability, stalls, groundwater handling, which EASA has a bit differences. They call it ground handling characteristic, but Part 25 also cover ground and water. And then there is miscellaneous requirement. So that is for Part 25, which is large transport aircraft. For the unmanned, we do have for unmanned the light unmanned mass, which is less than 600 kilo, if I'm not mistaken, which is there is a mass CG, approved flight envelope and environmental condition, performance data, controllability, and maneuverability and stability. And also for the larger unmanned, which is can go up to close to 20 ton, 20,000 kilo, which is receptors of mass and CG, a profile envelope, performance data, minimum speed, takeoff and minimum performance, climb requirement, rate of descent performance, performance and flight characteristic, requirement for flight in icing condition, landing, controllability, stability, vibration, and buffeting. So if you look at these standards across the table here, we do have basic, which is RKO, Annex 8, Part 3, and we do have Part 25, which is national standard for the US, and we do have EASA Part 25, national standard for EU. Then we do have also small unmanned published by EASA, CS, like UAS, medium risk, and also the JAROS, we bigger unmanned aircraft. So if we look at this across, I think we can find the similarity, even there are some differences in the subtopics. However, if we go into the detail of each of the subtopic, basically we arriving to the same result, which is the aircraft flights, performance, control, stability, maneuver. So those are the basic content of Subpart B. I'll go through a bit deeper later. Okay. For us, if you are designing new aeroplane, you may, for our level, we may go into this unmanned because that is, I think, the best the Malaysia can have at the moment. But for the larger transport aircraft, Part 25, we may dealing with this when you work for the design organization approval, when we do modification or major repair. So that is the level that we can go at this moment in Malaysia. But no issue on unmanned. I believe that is something which is less complex and also less cost. So I'll try to keep some example. For the large transport aircraft, we will try to also discuss on modification, big modification, and how the modification affected this design, affected this airworthiness standard, and which we as engineer working on the designing the mod, the repair, need to look at this airworthiness to ensure we still comply, because when you do some mod repair on the aircraft, we may nullify the COA until the mod and repair is approved by the authority. Okay? Any question, you can stop me. So let's go into a bit more deeper in brief, and later I go deep into the actual standard, and I'll try to read through some of it and stop on the subtopic which is important in the perspective of our current activity in Malaysia or other part of the world. Mostly not design, not OEM, mostly repair, mod, or STC. So when you look at genre, there are subtopic genre. There is the number 25.21, proof of compliance, 25.23, load distribution limit, 25.25, weight limit, 25.27, the CG, 25.29, empty weight and corresponding CG, and 25.31, remove ballast, and 25.33, propeller pitch, limit, and speed. So that is the subchapter. Okay, subpart, subtopic, and subchapters. So every one of these, there is a requirement of what need to show compliant. So the designer need to show compliant to every paragraph. So the number 25, 21, 25, 23, 25, 25, we call it paragraph. So we need to show compliance to each of the requirement in this paragraph. So, okay, so for example, pro or compliant should be by analysis when test when it's required. Then when you load distribution limit, you need to also distribute the load in the aircraft accordingly and limit to that distribution. Weight limit, we also need to establish. In this weight limit, we need to establish the maximum and minimum weight of the aircraft you design. But if you are doing modification and repair, you also need to state the maximum and minimum weight that repair or the mod will be introduced to the aircraft. Once you have the weight, you need to calculate, and then you need to weight the aircraft, and need to calculate the center of gravity. For the modification and repair, you need to establish new CG, or if the repair and mod is very insignificant in terms of weight, you need to prove it by weighing the aircraft and calculate the new CG and show that there is no change in the CG. But if you're heavy mod, like you're doing a cargo, you cut the cargo conversion, for example, heavy mod, and you may also install another engine, a new type engine or something, then that is a major mod. Then you have to see for the modification to see you are not far off, or you not be outside the stated empty weight, the stated minimum weight and maximum weight which has the aircraft designed to. So that is 25, 29. Then ballast, if you're not able to put the CG properly, you are able to put the ballast. For example, this photo here show the ballast. There's a plate, lead plate, normally lead solid block as a ballast to ensure the CG are within the acceptable range. For any modification or repair, you are still to do the weight and CG analysis. You weigh and calculate the new CG, but if you're not designing new aeroplane, you need to make sure that CG that you come up with after you do the mod repair still within the range the aircraft is designed to. So 25 to 9. So I'm also will show some example on if you do mod, you do repair as well as new. If you're doing new aircraft, for this situation, for example, when I was doing the Eagle, we specify what will be the maximum weight that we are designing the aircraft to. So when I was working for the Eagle, we specify the maximum weight, even though we may not fly that weight or you may not operate in that weight. However, for us to be safe, we go into the maximum weight that we can possible do, and then we do all the analysis and test the weight so that we have some reserve or we have some margin. If there are any requirement, you need to increase the weight, or for some reason when you do complete the aircraft is heavier than what is supposed to be, we already cater that maximum weight that we are able to do, or we want to do. Okay, so the diagram here, how important is CG? Because we have forces in the aircraft. So the forces, we need to know where are the CG, which is where the weight will be centered to. And then all the forces from the wing, from the stabilizers will be countering the weight for us to make the aircraft float or float. So the sum of all the weight and the lift should be in equilibrium. And the CG for aircraft stability, we always put it in front of the center of lift, because if something happens, we always want the aircraft to nose dive. If you store the aircraft, for aircraft which is stable aircraft, the nose always drop when you store it, and then the store will be almost automatically recovered. So that's what the rule Normally we put CG in front of the center of lift. So that is for the use for the aircraft maneuver, control, and stability. So, and then why the CG is important, because you want to operate within the allowable CG, or as you, if the CG, if the weight too far back, or the CG change too far back, and then you're not able to counter the forces to down to dip the nose, to lower the nose. So we don't have enough forces to lower the nose, then we got a problem. That's why the CG is designed within the limit where your control forces are able to maneuver the aircraft. Similarly, if the CG is too much forward, you're trying to be nose dive, so you have to have enough elevator force to actually to lift up the nose. For the case of 737-8 MAX, for example, there are some modification on the engine, and then the aircraft tend to dive nose down. So that's why they install the software, the computer system, the software, to when they when they have experience nose down, then the computer will correct it to bring the nose up. And that become a confusion to the pilot and cause few crashes. And also the last one, propeller speed and pitch limit. You need to operate within a allowable speed of the propeller. If the propeller speed is too high, you may have vibration or you may break the propeller. Because at propeller, the tip will easily reach Mach 1, which you have shock wave and you create vibration. The pitch limit is how much you allow, because you don't want to store the blade. So the pitch limit will be the maximum lift you get from that from the blade of the propeller. So those details in the 2533. Okay, any question? So it's really engineering. That's why if someone asking me why engineering technology are not really able to get a job in the designing of aeroplane, because you miss this chapter, subpart B. Similarly, mechanical engineer. Why we still need aerospace engineer? Because aerospace engineer will learn this during the school days. Mechanical do not have this. So that's why we still need aerospace engineer or aeronautical engineer to work on subpart B. Because subpart B is aircraft performance, stability and control. We only learn it in the aerospace or aeronautical engineering degree. There are people questioning me, say why we not let, for example, engineering technology student to work with DOA. So that is one of the reasons, because they don't have enough knowledge and competency to do this subpart B, to show compliant the subpart B flight. Okay, next. Next subchapter is about performance. The performance of the aircraft will be stall, takeoff performance, the takeoff speed, accelerate in stop distance. You accelerate, you stop, you still have enough runway left. You have to have safe distance. So that's accelerate, stop distance. So what are the remaining balance of the runway? There is minimum requirement for you to have the balance. Otherwise, you are unable to go to the runway, to use the runway, or you may want to redesign the aircraft as new. Takeoff path, as you take off from your movement in the ramp, Timex, pre-takeoff until you start takeoff. In the takeoff will be as you take off, pre-departure, you are climbing, you have few stage climbing. So along the way, we call it takeoff path. Takeoff distance and takeoff run off. So how long the aircraft stay on the ground before it rotate and lift up the ground and clear a 50 feet clearance, if I'm not mistaken. Then takeoff flight path. Climb. Then after you take off, you climb. You have maybe stage climb or you direct climb. So you need to have the climb rate. You have to develop the climb rate. And then once you cruise and then you land, you need to have landing, climb record, and also you need to also during this compliance, you also need to show the engine operating condition, all engine operating, and also we need to look at the climb performance, one engine inoperative, and also the en route flight path, and then last one is landing. So these are all the analysis here. The test analysis done in this subpart is about aircraft performance from the takeoff to land. Okay. Then subpart on this is on takeoff. You can see you roll on the runway, you go to V1, you rotate, and V2. Okay, you go to V1, pass V1, no chance to stop, and then you go to V2, you rotate, and then you clear your clearance for takeoff. Okay, takeoff clearance at the end, 35 feet. So V1, you may, if V1 is low, then you accelerate or engine running. When you reach V1, you having problem, you can stop. Okay, so you end up with some part of the runway, and then that also part of accelerate and stop test where you should have enough balance in the runway. Or as V1 low, you go VR and then you continue until you achieve V2 and you rotate. So that case acceleration, one engine out. So means that after you do V1 low, you continue, you rotate, V2 rotate and take off. So you are need to look at whether you're able to achieve this with one engine. Okay. So the green one is the distance for you to accelerate in all engine. The yellow one is accelerate in one engine. So there is provision. For that, either you need to check your all engine in operation and one engine out of operation, or some engine out of operation. You need to consider that. You need to have the data for that test as well. Then this is a flight path, flight profile. So the flight profile from takeoff, and then you climb to the cruising altitude, and then you fly, continue flying en route, then you descend, and then you land. But you also need to have consider to divert if anything happen. If the airport is having something on the runway, maybe there are aircraft on the runway, maybe there is a weather problem, whether there was any disaster at the airport area, then you cannot land to the airport. So you have also to consider for you to do the diversion. So that is diversion range, diversion time. You need also to calculate the fuel for you to able to achieve your diversion plan, diversion strategy. So this one I show you earlier. So accelerate, you rotate, you achieve V2, you rotate, and then continue climb. So here is landing distance. You land before you reach the runway, you have to clear 50 feet threshold to the touchdown point. So you need to achieve that, otherwise you are not, you will not certify for that to land. And the aircraft stop and it's in the ideal situation. So you have the end runway. So here is calculated landing distance, safety factor, because here you have to have, this is ideal condition to stop. You still have some margin here, so you can run over here and still have something there. So for here. Then we also look at the how this performance achieved. So this aircraft performance achieved through the wing and all the control surfaces. So very basic equation, which is lift. The forces over all the control surfaces or the wing are lift, which is the variable are the density, the rho here is air density, velocity square, wing surface area, and lift coefficient. This one is influenced by the airfoil cross section. So there's a table where you can get the CFL or lift coefficient, and this is based on the airfoil shapes and airfoil profile. So this is the basic equation. So aircraft forces, aircraft able to stay to provide the wing to provide the force is just through this basic equation. So lift coefficient, half of the density, time velocity squared, time the wing area. So for example, and also drag, also the same formula, only the changes is the drag coefficient. So CL is lift coefficient, for drag is drag coefficient. So for example, you're talking about, if you look at some incident, there are cases accident occurred because they forget that they add the density. They fly at very high altitude, the density is low, the flap setting is the same as you flying at the sea level. So they try to run over the runway, they cannot even achieve V2, and they try to rotate, and then they usually crash into the inner runway. It was a cases occurred in the country like with high altitude airport. And also speed and able to achieve the, enough velocity, and then also will cause it to crash. And the lift coefficient, you can't control it. You can control it, that's why you got slat, you got flap. When you operate the slat and flap, your wing profile, fall, or the complete wing will change, and then will increase the lift coefficient. So you increase the lift coefficient, you are able to control your density. Density will be a sea level where you're operating. You're able to speed up the aircraft using your engine from the thrust at some speed or very high speed. Then you also have enough surface area. Enough surface area is calculated. That's why when you're doing takeoff and landing, you have to down your flap, which will increase the surface area as well of the wing section. So this is a magic formula or magic equation which is used by this aircraft technology, and that's why the aircraft flying, because we have this formula. So the drag will also be the same. The drag will be the killer because the drag will be dragging out. So the drag and the lift will be in equilibrium for us to do the flight. So drag is always a problem. So still density, velocity square, the area, either the weighted area or the frontal area, okay, divided by 2, and also the drag coefficient. Drag coefficient depending on the shape, size, and frontal area of the aircraft. Okay, any questions? No? Then we also have this next is subchapter talking about controllability, maneuverability. How to control the aircraft. What kind of control you need? You need to have longitudinal control, which is pitch up and down. You need to have the directional control, your left, right. You need to also have lateral control, you can roll. And also you need to work on the minimum control speed. The minimum control speed, if you look at the formula this again, because there is a limit to the V here, so you need to calculate, or you need to do the flight test, what is the minimum speed that you can have for the aircraft to have the lift. So this kind of dangerous test, but we need to do the test. We need to determine what will be the minimum speed for the aircraft. It's almost stalled for us to be able to get the lift. So if you go beyond that, you will not be acceptable to fly the aircraft. If you cannot get that velocity, the speed, then you cannot fly the aircraft. For example, the Air India, they lost the thrust. So they lost the thrust, they end up with the slowing down the aircraft and also the increase the drag. So slowing down the aircraft will be the issue. That's why they're not able to get the lift required and then they crash. So control maneuverability. So control, you can see we have control surfaces, aileron, to roll the aircraft, flap actually to slow down the aircraft, to increase the chamber, slack in the front, flap and slack may be worked together to increase the wing platform area and also to increase the camber or the airfoil to change the lift coefficient or the airfoil for the aircraft to have better performance in takeoff and landing. And then we have rudder to control the aircraft, directional control, and elevator to pitch the aircraft up, down. That is longitudinal control. So just I'm like explaining to you about aircraft design here so far. Then why we need those? So what will be the forces? So what we need the forces, there is this aircraft is a body suspended in space. So we do have all these forces. We may have moment, you can pitch the aircraft nose up and down. You have moment over the wing. You have moment over that line, okay, that center line. Then you have this 6 degree, 1, 2, 3, 4, 6 degree of freedom, suspended in space. So what happened is you can see on the right diagram, there's airfoil as a flow over an airfoil. As flow over a surface, there will be a force perpendicular to that surface. That is fluid mechanics, fluid dynamics. The physics is, the science is as anything flow over a surface, so it will be a force generated 90 degrees to the surface. So that is how the airfoil been designed for a flow over it, and the flow over it cause lift. And they know that the camber also will affect on the lift coefficient, mean the lift will be affected by the camber, the profile. Then that's why they have many options for the camber and profile, airfoil profile. So down here you can see how the lift in the slack, in the flaps, maybe you have double flap. So flow will be inside the flap, slack, also inside the flap. So there's a flow. First, we'll reduce the flow separation, increase the flow, re-energize the flow, so we're able to maintain the lift efficiently. Okay, next is trim. So you need to trim the aeroplane because you are unable to just control this, control the column and then start to maneuver manually. So what we do, we just use trim for certain forces for you to be able to trim the aircraft condition. So that's trim 25161. And also we talk about stability. There's a static longitudinal stability and static lateral stability. So you look at this, if you study the detail, this is body and space. So this body and space, you have all this motion. We have roll, we have yaw, so we have pitch up and down, and also we do have for every forces here or every line reference here, we do have also torque. So we need to ensure this body is stable. That's why we need to look at the static longitudinal stability, demonstrate static longitudinal stability by test, and static lateral directional stability by test and analysis. Also, there is dynamic stability. So there are 1, 2, 3, 4. It's 1, 2, 3, 4, 5 subparagraph discussing about stability. So what is stability? Stability is something that we learn as you apply the forces. At the end, it becomes divergent, not convergent. It is convergent, not divergent. Means that as you apply the force, you apply 1, 2, 3. At the end, it becomes you finish. The amplitude becomes 0. Means that is that is stable. Static dynamic stability. It doesn't follow. If you got become diverge, as you apply the load, then it become more and more and more. That is that is unstable situation. Okay. So we need to control the aircraft we need to ensure the aircraft is stable as well. Aircraft stability basically caused by the design. For example, you have dorsal fin, you can see on the aeroplane. Those impact the aircraft stability. So static stability is something always people get confused. Dynamic is if you take time for you to become stable. Static just a few amplitude then become stable. So there's a difference. For example, here static stability refers to how quickly it return to the original state without taking into account of time. This pertains to factors like pitch, flow, and yaw. But dynamic stability take into consideration the changes over time as the aircraft return to equilibrium. We focus on the rate, magnitude, and nature of the acceleration that occur during the process. So that is the static stability and dynamic stability. So again, there is some definition of static and dynamic stability. There's even more because something subject is easy, really difficult to understand. So also you can see that what is the static stability, what is dynamic stability. So you need to have time to basically to diets of this signal. So stall. Next is stall. We are talking about 231 stall demonstration, which is test. Stall characteristic. So when you go into stall warning. Stall warning you install indicator on aeroplane, or you may also use a stall warning in terms of the aircraft behavior. How you fly the aeroplane. So aircraft, as again back to the equation, where as a fluid flow over a plate, you have force 90 degrees to the plate. Similarly here, as a airfoil, the air flow over the airfoil, then you got lift. So you also have angle attack. If you want to get more lift, you increase the angle attack, you will get more lift. However, if you got too much of the angle attack, the flow becomes separated and you stall the aeroplane. So the aircraft stall when the flow separated in the wing do not carry more lift. So that's a stall. So stall characteristic, also you need to see what happened in stall. When I was working for the Eagle, when they redo the wing, when we fly, and we stall, and the wings, one side of the wing drop. So that is the case. If we allow it to happen, the aircraft may go into spin. That's why we delay the separation, because the problem is separation. We delay the flow separation by installing vortex generators and boundary layer fences. So we need to delay. We need to prevent the separation of flow. There's also someone putting obviously the vortex generators is one of it. Some also design suction. So the air, there's many holes here on the wing surfaces, and they sucking out the air inside here, so you can see the flow will always attach because that is a flow going into this part. So stall warning. Stall warning. And we ask why Eagle having two wings, because the idea we don't want to stall the aircraft. So impossible not to stall the aircraft. However, the by wing that we have at Eagle, we store the wing first, and then as the first wing store, the second wing will not store, and then we correct it by as the nose dive, and then we recover the store from the first wing. So that's why you can say Eagle never able to store because of that situation. After stall, here is some example of the engineering, the angle attack, and lift coefficient. The lift coefficient maximum will be on top of this peak, and also the stall angle. So the more you get into the angle, the more you get, but at one time you got a place where it will be saturated, or where it will be the maximum. And if you increase the angle attack further, you may have flow separation already. So that's why we had to understand this curve here from the test has been done by the scientists, as well as and the angle attack that minimum or maximum you can use. So this equation of V stall, just similar equation. This basic equation will be half rho V square S CL earlier. However, we work out the V store, we come out, we remove this, we bring out this V velocity, and then we left the rest of the term remain. So this become the formula for the store speed. For the store speed, yeah. So this is how we calculate store speed. And this calculation for certification, you need to do tests. So what happened here, we in the Eagle experience, we do have stall at 45, 4.7 knots. However, the JR LSA, no LSA, VLA, the JR VLA, very light aeroplane, says that the stall should be 45 knots less. We're not able to get the 45 knots, we always get 47 knots. Then we got problems, so that's why we pull back the aircraft from the US, and then we repair, we modify the wing, so we get that 4.5, 45 knots stall. Okay. So, and then next one is a ground and water handling. You already have discussed on the air handling, stability and control, but now we also need to aircraft to be stable on the ground. We do have also need to check longitudinal stability and control, directional stability and control, whether you have your steering, okay, on the ground, and taxi condition, wind velocities, what is the minimum wind you're allowed to land, spray characteristics. So we need, if you are land in water, we should not allow the engine ingested the water. So that's why you need also to test the spray characteristic, control and stability on the water. And also another thing in miscellaneous. Miscellaneous is issue of vibration and buffeting, high speed characteristic, out of trim characteristic. So vibration and buffeting is common for the structure, especially when the structure speed become very high, it reach Mach 1, then very high speed. Behind the Mach 1, you always have this shock, and the velocity and the behind here is causing the structure to shake, to vibrate. So that is buffeting, vibration and buffeting. So in this case, we will see this occur when you do high speed, and it will occur on the shock wave will occur, and then the pressure will be different behind the shock wave. That one cause vibration. The shock wave and the flow behind will cause vibration and buffeting. High speed characteristic, what happens to the aircraft when you do high speed? And also our trim, when our trim, what it can do, are you still able to control the aircraft? So this is miscellaneous flight requirement. So everything 2.1, 2.3, 2.5 will be test by test as well. Okay, any questions so far? Okay, after this, I would like to share you the complete Subpart B from FAA. I just browsed through to see what is there, and for us to have the understanding of what is this Part 25 Subpart B. Okay, let me unshare this. Unshare. Stop sharing. Let me start share, and we have this. Wait, let me open first. Copy. Okay. Let me share. Window. Okay. Okay, here. So this is Part 25. You able to see this?
Yes.
Okay. Let me put it a bit bigger, I think. So this is the content detail of the subpart. So we can see subpart B flight, performance. I just discussed about this. Control and maneuver, trim, stability, stall, groundwater handling, and miscellaneous flight requirement. Then you go into the text itself. I will highlight a few issues which is important. For example, proof of compliance. Each requirement by the subpart must be met at each appropriate combination with NCG. So this is tough. Why tough? Because you need to consider all combination. Minimum weight, maximum weight, weight with empty weight with passengers, weight with cargo. So all the weight condition. Combination of weight and CG. How many weight and CG combination you need to work? You need to operate the aircraft, and you have to show those by. You have to consider that in your analysis. Okay, second, by test. So mean that this is another issue. You have to show compliance by test. If which certification is requested or by calculation. The trick here based on equal accuracy. So this is something quite difficult to achieve, because if authority asking you what is accuracy of your calculation, then you start scratching our head and then better do tests. Or by systematic investigation of each probable combination of it. So there's another issue here, systematic investigation. So it will be a question. What is systematic investigation? Each probable cause. That's why some take faster route, they just test. So just show compliant by test. Okay. Then again, controllability, trim, stall characteristic must be shown for each altitude up to the maximum expected operation. So you need to consider 10,000, 20,000, 5,000, 1,000. You have to do those analysis for every altitude up to maximum expected operation. Do you have any issue of control, stability, trim, and stall at what altitude when you see a problem? So that is what it means. Okay. Then the parameter critical for the test conducted as weight. So what is a parameter critical? Weight, loading, airspeed, power, wind must be maintained within acceptable tolerance. So I mean that during the test, you need to consider the weight, you still consider the CG, you need to consider the airspeed, power, wind. So during the test. So that's why the test become very expensive and very extensive. Okay, then if compliant with the flight characteristic requirement depending upon stability augmentation. So stability augmentation system upon any other automatic power. Okay. Automatic or power operated system comply must be shown by 25671. So it's not part of flight, so 571 part of this flight control system. So means that they allow aircraft to have flight augmentation system and automatic system. Not autonomous. Someone working on a drone always get things confused with autonomous. It's autonomous. So means it's automatic, stability augmentation system, automatic, power operated system. So mean that your flight characteristic, your flight control system, you are allowed to use stability augmentation system, automatic system, power operated system. 25671, 25672. So you mean you may able to use autopilot. You may have MCAS. So the 737 it max using MCAS. So that is it could be stability augmentation system. You may consider automatic, you may consider power operated. I will consider more of this as stability augmentation system because as the aircraft nose trying to dive, nose dive, so the system will bring the nose up. So that is how the MCAS. I think that they will run. So I think that's how it works. Okay. And then meeting the requirement, the wind velocity must be measured at height of 10 meters above the surface or corrected for difference between height is which the wind velocity measured. So wind velocity of 10 meters above the surface also need to consider. We're talking about wind velocity. So we are looking at, I think it's crosswind. The requirement of this part also associated with icing. Okay. Condition applied if you can seek instruction fly into icing. If not, then you are not allowed to fly into icing. And then also maximum takeoff gross weight of 60,000. So this section applied only to a plane with one of the following. Maximum takeoff weight is less than 60,000. Okay. For G3 and G4. Okay, G3 and G4. We move on. So this one is, for example, A320, we got 120 tons. So this is in the proof of compliance. So what I would like to stress here is a test. Test is a must. Must be shown by test or by calculation based on equal inaccuracy. How we want to say that our calculation will be similar to what you did, what we get in flight. In test flight, very difficult. It allows that the provision given you that, but you very difficult for us to justify that it is equal in accuracy. Okay, that is pro compliance 25, 21. So that is something we need to remember. And when you do any certification for new aircraft, for repair, for mod, you may end up with a flight test. Our problem when we get Eagle situation, we get 47 knot, which we presented 45 knots. However, if we did not get that 45 knots, and then we end up to bring back the aircraft, and then we need to redo the wing, redo the design of the wing to bring down to 45 knots. That is almost 10 million Aussie dollars. So that's how expensive it can be because most of it will be flight test. Okay, load distribution limit, range of CG and range OA and CG, gravity, which airplane may be safely operated. You need to establish range of weight and the CG. Okay, in the load distribution. Then the load selection may not exceed the selected limit. So mean that if you select the limit is certain load, maximum, minimum, should not go beyond that in your load distribution limit. If you are working on the current aircraft, which you are just doing modification or repair, you should be looking at what aircraft has been designed to, what is the limitation, what are the declaration in design, their maximum weight, minimum weight. So this weight limit here, maximum weight, minimum weight. You must establish a maximum weight, minimum weight if you are working on new design, but if you are working on the current design to do repair mode, you must maintain the work within maximum and minimum weight. You cannot be outside this limit. CG, okay, CG, the extreme forward and extreme aft. You must establish extreme forward, extreme aft, because the CG will affect the control force, flight control force. Because the flight control having certain size and then also will operate within certain velocity, will also have certain profile for the C of L. So mean that lift half rho V squared SCL, and then that will be the force. So you should the effect of the force will be size in this case, the S. So the size, you have only limited size in your control surfaces. So we have limited size means you only have limited forces. So that's why we need to establish the forces that are available in these control surfaces. What is the extreme, what the extreme forward and extreme aft. For helicopter, there's also lateral CG. Lateral CG limitation. For the airplane, just forward and up. Empty weight corresponding CG, you must measure the weight. You must weigh the aircraft for you to be able to get the empty weight. Empty weight, you remove everything except fixed ballast, and you remove fuel, oil, hydraulic. Full operating fluid, including oil, hydraulic, and other fluid. So that is when you weigh this aircraft with this condition, you say that you have established aircraft empty weight. We need that because that is the basis for you to calculate in future when you add weight, you remove weight in aircraft, in operation, in service, mode or repair. That will be used, the empty weight will be used to calculate the new CG. And to check whether for new design, what will be the sizes of the control surfaces and where are their location. And for mod and repair, you should maintain within that level which has been designed by the type certificate holder by OEM. Removable ballast, I show you. Removable ballast can be used, may be used. Okay, some I saw some. I have bought some airline in Russia. I think we are on Tupolev 124. They ballast the aircraft using water, using mineral water. They bring bottles of mineral water which used to ballast the aeroplane. I saw them carrying it and packing it and behind the seat in certain location of the fuselage. So I believe that is a ballast. But ballast, fixed ballast, you should be a permanent fixed ballast. You should be secured to the where you are. You need where you need to put the ballast for you to be able. Why ballast and location? Why location is important? Because the mass of the ballast, time the location will be the moment. That moment will counter whatever moment that you have for you to be able to maneuver the aircraft. Anyway, go to propeller speed and pitch limit. Okay, that is I skip. I already explained that. And then 101 general performance. Okay, general performance, there are some here. For example, for turbine engine power aeroplane, relative humidity. So you must consider what are the humidity for the engine operation. So here give you altitude, give you the vapor pressure, specific humidity, and density ratio, and doing analysis of the engine. Then we do have also talking about stall speed. Okay, the stall speed, they give you the formula. You need to calculate this formula. You need to look at the velocity. You need to look at the mass. You need to look at the wing area, and from there you can establish your stall speed. And you must test this in flight. By calculation is a formula, but actually you have to prove it by flight. Okay.
Satu question, Prof. If this requirement can be shown via maybe dynamic fluid analysis in PC, is it still be required to perform test flight?
By rule allow, but the problem is when it come to insimilarity atas tadi. So
we have to
in accuracy. So that is a challenge.
Okay.
So very difficult to answer when we say. I also do not want to put my head say, oh, this accuracy will be similar. I mean, my analysis will be similar in accuracy as you do the test. Then I don't want to bet my life for that. I say here.
Okay.
Where is it? Test.
Ada
Yes. Calculation based on inaccuracy. Then there is accuracy to the result of testing. Oh, payah bang.
Komputer cakap okay.
Kalau
I mean, the part of the argument can be the composer says it's okay and the software is certified, so maybe we can hasten the development of
okay,
this aircraft.
it can. Okay, what you can do? Good question. What you can do? You try to prove your analysis is accurate
Accurate and
as to the test, but you need to do the test to show that. So you will shorten the test, correct? Because you need to do a test to show that this is accuracy similar to the test. But
okay.
still have to do the test to prove the accuracy to the test. Okay. Okay, remove balance, propeller limit, then we go into general here or the detail on the performance requirement for the ambient. Atmosphere condition and still air. And then performance to the relative humidity. So more detail here. Then talk about stall speed. There's a formula here, and also you need to do the test. This your question. The answer is we had the problem before. We need to have the aircraft to be at 45 knots. We flew the aircraft at 45 knots by the Australian test pilot authority. Okay, authority test pilot, and we sent to US. The US never get that 45 knots. Even tests also having different result because interpretation how to fly to song. That's the problem. That's it. That's the problem that we have. And then we have to bring back the aircraft. We need to spend money to redo the design all the way. So that we do not want to have that kind of problem. That's why we do tests. Even tests also we have that problem. Okay, so I think we need to be careful and just using all the software that we have to justify the design. So this is a takeoff here. I will not be too much on that. Mean that you have to calculate the takeoff performance, icing, non-icing condition. For this case, if you do major modification, you may change the weight. You may also affect the takeoff performance. That's what I'm trying to say. Okay, takeoff speed. That's why we are not there yet to do like big cargo conversion. We just use STC because they already know how to because they have done all the flight performance. So they have to do another flight performance. This something happened before in one of the modification. When they completed the operation, aircraft operation, the whole cutout cracks. Aircraft was grounded. And then to fly again, because why? When you do STC, for example, STC does not have information of what from the design. So they do reverse engineering. So that somehow the reverse engineering is not successful, and then the cutout fail, and then they have to they have to test the load on that cutout, and then redesign, and then install a new cutout. Okay, so it's very expensive. Accelerate stop distance. Normally we use this to do the balance field length to calculate whatever remaining. Okay, this is very detailed here. So this is the tire pressure. Also, we need to consider right runway braking. Okay, then tire pressure, maximum braking coefficient to be used. And then you need to use the type of anti-skid system if you have. And also calculation on tire pressure, braking coefficient, tire to go through ground. Takeoff path, as you take off, what is your distance over the takeoff path? So takeoff path extend. For standing start to a point in the takeoff which airplane is 1,500 feet. So that will be takeoff path. Above the takeoff surface or at which transition from takeoff to en route configuration complete. Okay, so this is you need to do the flight test on this as well for your takeoff path. And there's a lot of parameter here we need to consider in your test. Then talking about takeoff distance, takeoff run, you need to calculate the takeoff distance, your takeoff run for every weight condition that you looking for in operation. And then takeoff flight path again, and then we have climb, general climb. So compliant must be shown at each weight and altitude again, ambient temperature, humidity again. Landing climb, landing one all engine in operation. Okay, landing climb. Landing, you go landing, you descend basically, you're talking about descend. Then take the climb, one engine in operation. Okay. Then you cut off one engine, you only remove two engine, you cut out one engine, you take off one engine, whether you have the performance capable up to the altitude required, and then video en route flight path. So for the en route, yeah, yes.
No sir, I was curious about something but tak apa, nanti panjang.
Tak apa boleh. Ah.
No, regarding aircraft performance, so essentially it is saying that it is better to have more engine rather than two or one.
Okay, not exactly. We need to see your operation, whether you have problem, you are not safe with one.
Okay.
Okay. If you are safe with one, and then you can prove your engine is super efficient, super safe, it's okay. Now now the design concept has changed to the risk-based design concept.
Risk-based design, yes.
So if you show your risk is less, then it's okay. You know the MI 171 does not have double hydraulic system. The requirement requires two independent hydraulic system, but MI 171 before, I don't know about the current one, only have one system. So they still fly.
But they managed to prove that it is safe, so it's fine.
They say they are safe, even though they do not really show the statistic they are safe, but acceptable for them for that kind of operation. But FAR Part 29 does not allow that. That's why we did not accept the aircraft. But people may say that, okay, what's the problem? And now we got 171 in Malaysia and they all still fly. So we can take the argument, but again, as we do the engineering, we need to provide hard evidence. That's a problem.
So the best way is redundancy.
The better redundancy, but again, also when there's something people miss. When you design aeroplane, we need also to think of the cost, operating cost, acquisition cost, buying the price of the aeroplane. We need to balance between the cost, operation, and safety. Otherwise, if everything two engine, then you just want to fly Ipoh Kuala Lumpur, for example, then that's why the Cessna Caravan is a single engine, can operate commercial. Yeah. Okay. Thank you for the landing. Okay. Landing condition, icing, non-icing. And then how to approach and what is your speed, everything. So that's why this costs a lot of money and very extensive. We do this first before we do anything. This is the first thing we do in developing aircraft, Subpart B first. That's why if you're looking at my experience with the Eagle, we just build the Eagle using fiberglass, and then the frame is plywood. We need to have the shape, and then the aircraft is strong enough for us to fly, to collect this performance, stability, control. But it's not for structure, for not that yet. We need to collect that information first. And from there, we start the detailed design. So control, aircraft must be safely controlled. The word is simple, safely control and maneuver during takeoff, climb, level flight, descent, and landing. And prove it. The proving is by flight test. Then a lot more detail. And then here, the following, okay. The following the table prescribed for conventional wheel type control. The maximum control force permitted during testing. Okay, this is control first if you do your roll. This is what the force is per pound. For short-term application, for pitch roll, two hands available for control, 75 pounds for pitch. For roll, 50 pounds. For short-term application for pitch rule, one hand available, pitch 50 pound, and roll 25 pounds. Mean that if you're not able to rotate, you're not able to handle that control surface, you cannot able to pitch the aircraft at 75 pounds, and then certification will fail. Because that is too hard to handle, too much force required. So this is conventional, but nowadays assisted, fly-by-wire, actuator, and all this stuff is still applied here on the design of the system. Even though it's not for the human, but if for the system, should be able to have these kind of forces. Okay, here is this is a force impound applied on control wheel, rudder pedals, yaw control, yaw left and right yaw, 150 pound, for long term 20 pounds. So this is a detailed design you need to work with. And then wheel speed. This is a detailed maneuver capability and constant speed coordinated turn for CG. So the details here. I do not want to go through, it will be very long. But however, I would like to show you this is the engineering that we need to do for the certification for flight. Longitudinal control, okay. We have this directional lateral control. We have this minimum control speed. Minimum control speed, again, this is almost stall. Stall, you have no more control. So that's why when you stall, for example, when we store the eagle, we stall, we do not have the control. First, we need to see is first we need the requirement for the flight test, we need to identify it is stalling. If not, we got problem. We're not aware it is stalling. And then immediately after you stall, the best design is the nose to start to dive. When the nose start to dive, start picking the air start picking the air, and then they regain the lift. So if you are not able to nose dive, we can continue nose up, then you'll be into deep stall. Or for our case, our experience is the wing drop on one side. Wing flow separated in one side earlier than the rest. So we need to re-energize the flow to stay over the surface by installing voltage generator as well as relay fences. And we did that, we achieved that. We did that, we stopped, we did not get that wing to drop left or right. So that the fake is there. But however, the wing we cannot clean because there are VGs and also one relay fences. And extra maintenance as well. I have to look at those components. So that's minimum control speed is the same. What is the speed? Is still able to have all the forces. Mean that this is speed we have because aileron is F1, elevator is F1, rudder is F1. So again, if you store that, you have normal lift. So what is minimum speed before you store? You still have the forces over those F1. So that is the test you need to do. Very dangerous test here. Then what else? We do need to see the trim. Obviously trim, lateral trim, longitudinal trim. Because trim is issue where you need to have proper trim because we do not want to make the pilot tired, and then that could be human factor issue. So that's why we need become important that we have this trim system in place. So I say each plane must meet trim requirement of this section after being trimmed and without further pressure upon or movement of either primary control or their corresponding trim control by the pilot or automatic pilot. So we do not want the trim basically, to me, is human factor issue. We do not want to stress the pilot, so let him fly comfortably. So we use the trim system rather than he is controlling the whole control spaces. General stability, longitudinal static stability. I'll show you the diagram earlier. Demonstration of static longitudinal stability. So you have to fly the aircraft, you have to climb. Okay. And also you need to measure the slope, the speed. We need to put in the the chart that I show you, you need to create the chart. And then the trim is the flap retracted, landing gear retracted, is trim width, the control stick forces might able to have slope is a percent. So this is another condition. Cruise, okay, climb, cruise, we need to show that climb, cruise, approach, landing, and then static lateral longitudinal, static lateral stability, the directional stability. Also, you need to test. Also, you need to test for the side slip angle, dynamic stability, store demonstration, power off, power on. This is all the characteristic. Store characteristic. Then it must be possible to produce and correct roll in yaw bar and reverse use of aileron, rudder control, upon the time the airplane is stalled. No abnormal nose up pitching may occur. That's why we want to put the CG forward so it will pitch down.
Make the nose heavy.
Make the nose heavy, correct. The longitudinal control force must be positive up to the throughout the stall. Okay. So this is the thing you need to show. Stall warning. Stall warning must be sufficient margin to prevent. Okay. You must have warning. Within, okay. Warning. Must be clear and distinctive to the pilot in straight and turning flight. The warning, eh? The warning must be furnished either through inherent aerodynamic qualities, airplane, or by deviate device. So you can have also aerodynamic qualities, mean that when you fly, you feel there's a stall, you know it's a stall. There's a sign aircraft is stalling, or a device. Normally we take the device. Okay, so then stall, we go into the detail of the stall itself. Is I said again, this one is 10 million. So how extensive the stall should be. Longitudinal stability control. Okay, then directional stability control, ground and water. So this is not fly, ground and water handling characteristic. Longitudinal stability control, we don't want when you on the ground and you become the undulating,
Oh,
undulate up down, and then when you do the turn, the aircraft skidded into the grass or something like that. So directional stability control, longitudinal stability control, taxiing condition. So example, the shock absorbing mechanism may not damage the structure of the aeroplane when the airplane is taxied on rough ground. So that is something you need to do. This requirement also part of the structure design. Wind velocity for land plane and amphibian, the following apply. The 90-degree cross component of wind demonstrate to be safe. Okay, crosswind 90 degree. For takeoff and landing must be established on the runway, must be at least 20 knots or less. So mean that you need to establish at least 20 knots. Crosswind, 90 degrees. This one of it. And icing condition, non-icing, and also seaplane requirement. If you design for EASA, they don't have the discipline, only ground. Spray characteristic. Okay, seaplane, this is for seaplane or amphibian during takeoff, taxi, landing in the condition set for. There may be no spray characteristic that will impair pilot view, cause damage. So mean the pilot view, you cannot impair the pilot view. You cannot get the engine ingested, the water ingested to the engine. So that is a basic spray characteristic, control and stability on water.
Does it still apply to STC? For example, there is an aircraft, caravan, sea operating. So the float or pontoon is by STC. So, therefore, I'm not sure whether it complies to.
If there is already STC installed, mean they already have the test. 25239 has been done.
Okay.
So because you are not, unless you are modifying the aircraft under Malaysian DOA to install the pontoon, yes, then you have to do 25239.
But itu kira local
No.
mod lah.
Yes, correct. If you just accept aircraft with ACC for amphibian, you just install because your work is only to fill up the form 1.
So local mod that's between us and CAM.
Yes, local mode, you can do that. However, you need to look at all these to 25239, also longitudinal stability, static stability, empty weight. You have to go back the whole Subpart B because pontoon extra weight.
Tapi Malaysia, but then Malaysia can adopt code from other authority lah.
There, yes, Malaysia can adopt code validity, correct. I mean, if your DOA having the scope of approval, then okay. But I don't think we do have that scope of approval now.
Yes, tak ada.
So that is another issue. Okay, good question. Vibration buffeting. Okay, airplane must demonstrate the flight to be free from vibration buffeting that would prevent continued safe flight and any likely operating. So the word is only there, vibration buffeting. Buffeting, the wing skin start to flap off. Vibration could be from engine, could be from motor, could be from anything. Rotating equipment. Buffeting is the skin structure itself become flip-flop. Okay, so that's it. So this is the basic vibration and buffeting. High speed characteristic, speed increase and recovery characteristic. The following speed increase and recovery characteristic must be met. Operating condition and characteristic likely to cause inadvertent speed increase must be simulated in the airplane trim at likely cruise speed. So any action which inadvertently increases speed. Okay. Inadvertently increase speed. For example, you do the turn, suddenly the speed increase. Then you have to show. You have to show whether they occur or not. If not, not applicable. But if there is any tendency in flight, the speed tend to increase in certain activity, then you have to do 25 to 53 high speed characteristic. And last one is now almost 11. Last one will be out of trim characteristic. For any initial condition with the airplane trim at cruise speed, airplane must have satisfactory maneuver, stability, and control with degree out of trim involve airplane nose up and nose down. If you are out of trim, you still be able to maneuver you must have satisfactory maneuvering, stability, and control with out of trim condition. A 3-second movement, so those are the details are here. So all these are flight tests. So what actually I'm trying to show you is we are not doing new aircraft, most of us. We may use this to design unmanned aircraft, that is possible, feasible and possible. So if you want to design a new aircraft, unmanned, and then this has to be satisfied. So what is the most important thing that we need to think here? We need to think we should have enough budget because a lot of tests to be done here. We should also think there are risks that can occur if any one of these fail. Performance, control, trim, stability. Because the aircraft are manned, nobody on board, still the aircraft may crash into someone's home, someone's houses. So that is what it means that whatever you do, manned, unmanned, you still need to look at this. Only the complexity could be a bit different. That's all. Secondly, if you do more, you are airlines, technical services, or DOA. So this is the flight part. This is the flight. If you involve any mode, end up with doing flight, Subpart B, this is the area you need to choose to show compliance. And also you need to think how complex it will be, whether you have the competency to do that, whether you have the budget to do that. For example, talking about float again. So you have to do all this. Flight general, yes. You have to do performance because you do not know how the aircraft will store with the float.
It came with a whole tick supplement.
Yes, correct. It could be control. You have no control now because you already have something putting on board. Even though there's already aircraft with a float, unless you got the data from them, that is no requirement. But if you are installing new float, that's new float, new type float, new material, new weight, then you have to do all this. Everything. Okay, So I think it's already 11 to 11. So I think I open up this for discussion, questions. If not, I can end this session and I will start. I will also do Subpart C and I will finish with Subpart H later. Hopefully by the end of the year, I can finish all A, B, C, D up to H. And hopefully I'll put this in video so someone may go and revisit this in my YouTube channel. Okay, any question?
The moral of the story: certification of aircraft is expensive.
Yes, correct. Expensive one. And when you want to sell to another country, they will do this again for you. I mean, for your aircraft.
Yes.
And then they may not be doing the whole thing, but they will select a few of these requirement
Oh,
here.
sampling.
Sampling. But what happen if interpretation are different?
Re-engineering, more money.
Need engine more money. So if you are thinking to design aeroplane, you may want to get the authority where you want to export aircraft to work together with you in the certification.
Yes.
That's the safest way.
But if you get this right, you'll be rich.
Not necessary. For big aircraft, I think it's not our level. For smaller aircraft, I'm not trying to be negative, but not much. I mean, you also in GA, right?
Yeah.
You know what would be the market like.
Yes.
So that's why when people come to me with proposal aircraft project, my first question, who are your customer?
With the shortage nowadays, I was thinking suddenly at one point I was thinking, would be nice if MD3 and Eagle are still in the market.
Uh, it is possible, but for that technology, I think
Yes.
people will buy. There's a problem. So the Eagle and the SM3,
Yeah.
MD3, the problem they have, they do not create a new product along the way.
Yes. There is no product along the way. Yeah.
Unless there are always a new product, new version, even simple design change, that will keep the product in the market. But but the possibility that we may do, could be a potential is electric aircraft.
Yes.
Because no one doing it yet, we can do it at a maybe competitive price because of the ringgit compared to USD and compared to EU or US, US, EU or Australian dollar, we are cheaper. We may able to cut down the development cost. But again, aircraft certification is state by state affairs.
Mm.
That's the problem. Okay, thank you, Cik Razif. I think you got your electric aircraft on this Aries E kasut. What happened?
Yes. For the kasut, but it doesn't go through very well. So
If you want, if you're interested to play around with electric aircraft, we do have aircraft EMIAT, the smart plane.
okay.
So we may form a team, MIAT and Plus Industry, work together. We try to install electric engine. At least the aircraft can taxi. That's good enough for me, I think, because
Okay.
it can be a training for the future module for
Yes.
15, 14.
Yes. I would love to
Ah.
join.
Then I will get the team to work together and to maybe it's a long-term team effort
Yes.
for the country, for the nation. At least if we can say we have electric aircraft taxi in Malaysia, then already a good news.
Get,
May attract investors to join.
the way I see it, getting the aircraft taxi not an issue, but
Yes.
component longevity, that's a whole another topic lah.
That if you got aircraft taxi, you mean that you have running engine,
Yeah.
you have the taxi performance, then you can learn from whatever we did. I mean, we have what we have done. You can learn from that for future development.
Yes.
So if anyone interested to involve to invest, then you already have the know-how. That's my thought. Okay, we can think about it. We also maybe contact Captain Imran.
Yes.
Uh, Okay, Cik Raziz, thank you very
Thank you,
much.
sir. Thank you, sir. Thank you very
If
much.
no one else, I will stop here. Thank you for your participation. Assalamualaikum warahmatullahi wabarakatuh. Good night.
Waalaikumsalam. Good night.
Night.
Thank you, sir.
Thank you.